In a clean room in Florida, wrapped in a nitrogen-purged shipping container that has already crossed an ocean by barge, sits a machine that NASA believes will rewrite our understanding of dark matter, dark energy, and the possibility of life on other worlds. And it is now fueled, tested, and less than a month away from leaving this planet forever. Its field of view is at least 100 times larger than the Hubble Space Telescopes. In a single image, it will be able to capture more sky than Hubble managed to photograph across its entire 3D career. And somewhere inside its instrument bay is a piece of experimental hardware so advanced that NASA is calling it the most sophisticated technology for directly imaging alien planets ever flown into space. This is the Nancy Grace Roman Space Telescope. And if you subscribe to this channel, you know we don't wait for the launch footage to tell you why a mission matters. We go behind the scenes into the clean rooms, the fueling bays, the decade of engineering decisions that got a spacecraft to the launch pad in the first place. Because the story of Roman isn't just about a telescope. It's about a woman who fought to get women into astronomy in the first place. A spacecraft racing 9 months ahead of its own schedule. And a fundamentally different way of looking at the universe that could finally answer questions Hubble and even the James Webb Space Telescope were never built to solve. By the end of this, you're going to understand why NASA built a telescope that deliberately trades Hubble's razor-sharp focus for something almost the opposite, a wide, sweeping panoramic view of the cosmos, and why that trade-off might be the key to unlocking one of the biggest mysteries in modern physics. You're going to learn how a spacecraft, nearly 18,000 pounds in mass, traveled from a clean room in Maryland to a launch pad in Florida by barge. Of all things, floating down the Atlantic coast like cargo on a slow, careful voyage. And you're going to hear about a woman named Nancy Grace Roman, a scientist so instrumental to the existence of the Hubble, decades before anyone thought to name a telescope in her honor. Let's start with the number that should stop you in your tracks. At least 100 times. That is how much larger Roman's field of view is compared to Hubble's. Hubble, for all its legendary achievements, sees the universe through something closer to a soda straw, an extraordinarily sharp, extraordinarily deep soda straw, but a narrow one nonetheless. Capturing its most famous images, the deep field photographs packed with thousands of distant galaxies, required pointing Hubble at a single, tiny patch of sky and staring at it for days, sometimes weeks, letting photons from galaxies billions of light years away slowly accumulate on its detectors. Roman flips that entire approach. At the heart of the spacecraft sits its primary science instrument, the Wide Field Instrument, a 300-megapixel infrared camera built with a field of view roughly 200 times greater than the comparable camera on Hubble. Rather than staring narrowly and deeply, Roman is designed to survey enormous swaths of sky rapidly, capturing the light of potentially 1 billion galaxies over the course of its mission, and doing it efficiently enough to complete surveys that would have taken Hubble decades, would have simply been impossible to attempt at all. This isn't a small technical upgrade. It's a completely different philosophy for how to explore the universe, and it exists because of a specific, stubborn mystery that neither Hubble nor even the James Webb Space Telescope, for all their power, were designed to crack. That mystery is dark energy, the unexplained force that appears to be accelerating the expansion of the universe itself. We've known since the late 1990s that the universe isn't just expanding. It's expanding faster and faster. A discovery so unexpected it earned its discoverers a Nobel Prize. But nearly 3 decades later, scientists still don't fully understand what dark energy actually is. Some possibility, some strange property woven into the fabric of empty space, is pushing galaxies apart at an increasing rate, and it appears to make up roughly 70% of everything in the universe, yet we still cannot directly detect it, isolate it, or explain it with confidence. To understand just how strange this problem is, picture throwing a ball straight up into the air. You expect gravity to slow it down as it rises, eventually pulling it back toward the ground. That's what astronomers assumed the universe's expansion should look like too. A big bang that flung galaxies outward, with gravity gradually slowing that expansion down over billions of years. Instead, when astronomers measured the brightness and distance of a specific class of exploding stars, called Type Ia's supernova, scattered across billions of light-years of cosmic history, They found the exact opposite. The expansion wasn't slowing down, it was speeding up, as if that ball thrown into the air kept accelerating upward, defying every expectation about how gravity should behave on the largest scales. That observation didn't just add a new piece to the puzzle of cosmology. It broke the puzzle entirely, forcing physicists to invent an entirely new concept. Dark energy, simply to describe a phenomenon nobody had predicted and nobody can yet fully explain. To make progress on a mystery this size, scientists don't just need to look deeper into space. They need to look at more of it at once, tracking how galaxies are distributed and how that distribution has changed across cosmic history. That requires surveying enormous volumes of the sky, cataloging tens of thousands of supernovae as cosmic mile markers, and mapping the subtle gravitational fingerprints that dark matter leaves on the light of distant galaxies as it passes through a phenomenon called gravitational lensing. Roman's senior project scientist has described the mission surveys as revolutionary, explaining that these observations are the keys that will allow researchers to unlock the fundamental nature of dark matter and dark energy and the fabric of the universe itself, according to the same scientist. The universe puts on spectacular cosmic displays every single second, but those events unfold so quickly, and across such vast stretches of sky, that conventional telescopes simply miss most of them. Roman's panoramic vision is built specifically to catch dozens of these fleeting cosmic events. History of the universe with a level of statistical power no previous mission has come close to achieving. That alone would justify the mission. But Roman was never designed to be a one-trick observatory. Buried within its science goals is a second, entirely different frontier: the search for planets beyond our solar system. And specifically, the search for evidence that we are not alone. Roman will conduct what scientists call a statistical census of planetary systems across our galaxy, using a technique called gravitational microlensing, a method almost nothing like the way most exoplanets have been discovered so far. Instead of watching a star dim slightly as a planet passes in front of it, the technique, relativity. When one star happens to pass in front of a more distant star from our vantage point, the nearer star's gravity actually bends and magnifies the light from the star behind it, briefly brightening it in a way that can be measured with extraordinary precision. If the foreground star happens to have a planet orbiting it, that planet leaves its own tiny, distinctive signature within that the planet itself is far too faint and distant to ever be seen directly. The catch with microlensing has always been timing and coverage. These alignments are entirely unpredictable, and each one lasts only a matter of hours, 2 days before the two stars drift apart and the effect fades. Watching for rare alignments that could happen anywhere within an enormous field of view at any given moment. Ground-based telescopes have attempted this kind of survey before, but Earth's atmosphere blurs and limits what they can detect, and no single ground-based observatory can watch continuously without interruptions from a million miles from Earth with an uninterrupted view of a single patch of sky, in a field of view broad enough to monitor hundreds of millions of stars at once. Is uniquely built to this technique is uniquely capable of detecting planets that other methods routinely miss, particularly planets orbiting far from their stars. Out where it's cold and dark, more like Jupiter or Saturn's distance from realize, it's already been tested in orbit. Tucked inside the spacecraft is an instrument called a coronagraph, a technology demonstration designed to do something extraordinarily difficult: block out the overwhelming glare of a distant star so precisely that the comparatively faint light reflected off any planets orbiting that star can actually be seen directly, rather than inferred indirectly through dimming or gravitational effects. NASA has described this as the most advanced technology ever flown in space for directly imaging planets around nearby stars, a crucial step in the broader search for life on other worlds. Directly photographing an exoplanet, rather than detecting its shadow or its gravitational fingerprint, is one of the hardest technical challenges in all of astronomy, roughly comparable to trying to spot a firefly hovering an inch away from the blinding beam of a lighthouse, from thousands of miles away. If Roman's coronagraph performs as engineers hope, it will pave the way for future missions specifically designed to image potentially habitable Earth-like worlds directly, rather than relying entirely on indirect evidence. That distinction matters more than it might first appear. Nearly every exoplanet discovered so far has been detected indirectly. Through the faint dimming of starlight as a planet crosses in front of its star, through the tiny gravitational wobble a planet induces in its host star, or through the microlensing signatures Roman itself will hunt for at scale. In almost none of these cases have astronomers actually seen a planet's own light directly, separated cleanly from the overwhelming glare of the star it orbits. Direct imaging changes that it would allow scientists to eventually study the actual light reflected or emitted by a distant world, potentially breaking that light apart into a spectrum and searching for the chemical fingerprints of an atmosphere, water vapor, oxygen, methane. The same kinds of signatures astronomers already search for using instruments aboard the James Webb Space Telescope, but applied to a world we can actually see as a distinct point of light rather than infer from a shadow. Romans. Coronagraph is not expected to achieve that final goal on its own. It is, fundamentally, a proof of concept, a chance to test the underlying technology in the harsh environment of space, working out the engineering challenges before an even more ambitious successor mission attempts to point that same technique at potentially habitable worlds. But every long journey toward answering whether we are alone in the universe needs a first working demonstration, and Roman is set to provide it. Here's where the story takes a turn that even NASA didn't expect a few years ago. Roman wasn't supposed to be ready this soon. Its official target launch date, set years in advance and repeatedly referenced in planning documents, was no later than May of 2027. Big, complex space telescopes almost never move ahead of their own timelines. Cost overruns, technical setbacks, supply chain disruptions. These are the forces that typically push launch dates later, not earlier, as anyone who followed the decades-long saga leading up to the James Webb Space Telescope's eventual 2021 launch can attest. Yet Roman's launch has been moved up to no earlier than Sunday, August 30th, 2026, arriving 9 months ahead of its most recent official schedule, and even earlier than a previously adjusted target date. To put that acceleration in context, consider the mission most people naturally compare Roman to: the James Webb Space Telescope, first proposed in the 1990s, endured repeated delays and ballooning costs for well over a decade before it finally launched in December of 2021, becoming something of a cautionary tale about how difficult it is to keep in a clean room in Florida, wrapped in a nitrogen-purged shipping container that has already crossed an ocean by barge. It's a machine that NASA believes will rewrite our understanding of dark matter, dark energy, and the possibility of life on other worlds. And it is now fueled, tested, and less than a month away from leaving this planet forever. Its field of view is at least 100 times larger than the Hubble Space Telescopes. In a single image, it will be able to capture more sky than Hubble managed to photograph across its entire 3DA career. And somewhere inside its instrument bay is a piece of experimental hardware so advanced that NASA is calling it the most sophisticated technology for directly imaging alien planets ever flown into space. This is the Nancy Grace Roman Space Telescope. And if you subscribe to this channel, you know we don't wait for the launch footage to tell you why a mission matters. We go behind the scenes into the clean rooms, the fueling bays, the decade of engineering decisions that got a spacecraft to the launch pad in the first place. Because the story of Roman isn't just about a telescope. It's about a woman who fought to get women into astronomy in the first place. A spacecraft racing 9 months ahead of its own schedule. And a fundamentally different way of looking at the universe that could finally answer questions Hubble and even the James Webb Space Telescope were never built to solve.